Before we jump into today's lecture, let's take a quick second and review some of the series tests that we've learned so far. The first one is a geometric series. Common ratio here, we have r is equal to 1/2. And so by the geometric series test, absolute value of r is equal to 1/2, which is less than 1, and the series converges. For the next series, it's the same geometric series as the one above it, only now it's alternating. So our r is going to be negative 1/2, and still the series is going to converge by the geometric series test. The series below it is a p-series. So we have here p is equal to 2, which is greater than 1, and so the series converges. In the series below it, it's the alternating form of the p-series. So it's not a p-series strictly speaking, so we can't use the p-series test, but it is alternating, and so we can use the alternating series test to show that this series converges. Now, intuitively, it should make sense that each of these starred series, that they would converge, because in comparison to the series that's right above it, we see that the terms are either equal or they're less than the terms of a series that we know converges, and the limits of both series is also equal to 0. So kind of a heavy argument, but strictly speaking, we can't use the comparison test because the alternating series do not have all positive terms, but intuitively trying to just make sense of the fact that if we know that a series where the absolute value of all the terms converge, then the alternating series would also converge. Now, the last series on the page, it's not strictly alternating, and so none of the tests that we have above will work for us. And so we need a new method to determine if the series converges or diverges. And the theory behind the series above, those ones converging, is the same as for the bottom series on the page. And so if we know that the absolute value of the terms, that series would converge, then it would make sense that this series converges as well. And that's what we call the absolute convergence test. The absolute convergence test tells us if we have the sum of the absolute value of a sub n, and we know it converges, then the series a sub n converges as well. And we can prove this using the comparison test. So let's start by absolute value of a sub n. By definition of absolute value, we know that it's bound by the negative absolute value of a sub n below and above by the positive absolute value of a sub n. And think of perhaps if we just had the absolute value of x less than or equal to 5, then that's the same thing as saying that x has to be greater than or equal to negative 5 and less than or equal to 5. We're just generalizing with our a sub n. Now, if we add a sub n throughout the inequality, then we get a lower bound of 0, less than or equal to a sub n plus the absolute value of a sub n, which is less than or equal to 2 times the absolute value of a sub n. And now we have two converging series. We know that since it's given to us, the series, the absolute value of a sub n converges, and so twice the series absolute value of a sub n also converges. And so by the comparison test, we have a sub n plus the absolute value of a sub n that's bound by 0 and above by something we know converges. And so the sum from n equals 1 to infinity of a sub n plus the absolute value of a sub n has to converge as well. So now we have two converging series. We have our a sub n plus the absolute value of a sub n and the series absolute value of a sub n, and they both converge. And so we can take the difference of our two series using our limit laws, and that tells us that our series a sub n must converge using our limit laws. For our first example, let's revisit the series from our opening slide. And we can determine now, using the convergence test, whether this series converges or diverges. Now, as it's written, as we mentioned previously, we'd have difficulty determining whether it converges or diverges because it's not a p-series. We can't use the integral test or the comparison test if all of the terms are not always positive, and it's not strictly alternating, so the alternating series test would not apply either. But with the absolute convergence test, we can look at the sum of the absolute value of the terms, and in this case, that would equal the sum from n equals 1 to infinity of 1 over n squared. And this we know converges. P-series, p equal to 2 greater than 1. And so our series converges, which then means that the original series, the sum from n equals 1 to infinity, of a sub n converges by the absolute convergence test. So if we have a series where a sub n converges and also the absolute value of the terms a sub n also converges, then we call that series absolutely convergent. However, if a sub n converges, but the absolute value of the terms, that series, diverges, then we call that conditionally convergent. An example of a conditionally convergent series could be the alternating harmonic series. So for the alternating harmonic series, we'd have -1 raised to the n minus 1 over n, and this series converges by the alternating series test. But if we looked at the sum of the absolute value of the terms, then this series is equal to the harmonic series, 1 over n, which we know diverges. And so again, the alternating harmonic series is conditionally convergent. In our next example, let's determine if the following statements are true or false. So in part A, we have the alternating harmonic series, and if we're given that converges, then the absolute value of the terms, that series, has to converge by the absolute convergence test. So now this is pretty obviously false, since we just did this example on the previous slide, but to generalize, what part A is asking is if we knew that the series a sub n converges, then does that mean that the absolute value of the terms, that series must also converge? And no. This is the converse of the absolute convergence test, which is not necessarily true. Can be, but it doesn't have to be, so false. Next example. Here we have -1 to the n minus 1 over n squared. This series converges, and so can we say that the absolute value of the terms also converges by the absolute convergence test? So here we have our a sub n would be the -1 to the n minus 1 over n squared. While this statement is true that both of these series converge, the overall statement is false because knowing that the series of a sub n converges does not mean that we can say that the absolute value of the terms a sub n converges by the absolute convergence test. And just like in part A, one does not imply the other, so this statement is also false. In part C, it is true that our geometric series converges. Here we have absolute value of r is 1/5, which is less than 1. And so we know that a sub n, the absolute value of those terms, converges. And by the absolute convergence test, that means that the series a sub n also converges by the absolute convergence test. And so this one is true. So we have 3 cases overall. If we know that a sub n converges, then the absolute value of the terms could either converge or diverge. We would have to do additional testing to determine which is the case. So the absolute value of the terms diverged. Think the alternating harmonic series. Over n converges, but the absolute value of those terms diverges. And so this would be conditionally convergent. Or, alternatively, if we know that a sub n converges, then we could check the absolute value of the terms, and that series could also converge. Think of our alternating p series, where p is equal to 2. This series converges, and the absolute value of the terms, that series also converges. And so in that case, we would say that the alternating series is absolutely convergent. Now, if you started with the absolute value of the terms and you knew that converged, then by the absolute convergence test, you know that the sum of a sub n must converge as well. And so again, this would be absolute convergence. So this is particularly useful when we're dealing with alternating series to determine if they are conditionally convergent or absolutely convergent. And absolutely convergence is a stronger condition. It's a stronger type of convergence than something being just conditionally convergent. And at the end of the lecture, we can talk a little bit about why you would care, the difference between the two series. In example 3, let's consider the alternating series, -1 to the n over n plus 2. And we want to know, is it absolutely convergent, conditionally convergent, or does this series diverge? So let's start with the alternating series. We know that it is alternating, and so that's a pretty good sign that we want to use the alternating series test. We need to prove 2 things. The first is that the limit as n goes to infinity of b sub n, so not the alternating part, but 1 over n plus 2, is equal to 0, and this is clearly true. And we also need to show that the terms are all positive and also decreasing. And in other words, that means we want to show that 0 is less than or equal to b sub n plus 1, less than or equal to b sub n. And in our case, our b sub n is 1 over n plus 2. And so we have 0 is less than or equal to 1 over n plus 1 plus 2, which is less than or equal to 1 over n plus 2. And this is also clearly true. It's really nice when you have the 1 in the numerator. If that is the case, then whenever you're taking the limit or trying to show that the terms are decreasing, there's really no work to show. You can just say that it is clearly true. And so for our conclusion, we have, since the limit is 0, it's the limit as n approaches infinity of 1 over n plus 2 is 0, and 0 is less than or equal to 1 over n plus 3, less than or equal to 1 over n plus 2 for all n greater than or equal to 1. It is important you need to make sure you include that step since it's not true for all n. Then the sum from 1 to infinity of negative 1 to the n over n plus 2 converges by the alternating series test. What this means so far is that we know at the very least the alternating series is conditionally convergent. But to determine if it's absolutely convergent, we need to keep going and look at the series 1 over n plus 2 and determine whether that converges or diverges. Okay, so to determine the absolute convergence, we need to know if the sum from 1 to infinity of the absolute value of our alternating series which is equal to the sum from n equals 1 to infinity of 1 over n plus 2. We need to know whether this converges or diverges. If it converges, then we would say the alternating series is absolutely convergent. And if it diverges, then we would say the alternating series is conditionally convergent. This looks a lot like 1 over n. So we'll do a little scratch work here. If we look at our leading terms for a very, very large n, we can compare this to 1 over n, and so that should give us the idea that 1 over n plus 2, that series diverges. But the inequality, 1 over n plus 2, is not greater than or equal to 1 over n. So we can't use the comparison test to the harmonic series. We need a different compare to series. To determine this, let's use what I called the finesse method from a lecture last week, which is just a really nice way of finding the appropriate compare to series when the sign, the plus or the minus, doesn't work in your favor. We start with 1 over n plus 2, and since we think this diverges, we know that we want it to be greater than or equal to. And while it's not true that it's greater than or equal to 1 over n, it is true that it is greater than or equal to 1 over n plus 2n. And by adding that extra n in the denominator, now we can combine like terms. So we have that is greater than or equal to 1 over 3n, and that is greater than or equal to 0. So that's our inequality, and we know our compare to series from n equals 1 to infinity of 1/3 over n diverges because it's harmonic. And so for our conclusion, we say since 1 over n plus 2 is greater than or equal to 1 over 3n, greater than or equal to 0. For all n greater than or equal to 1, make sure that you include that somewhere in your statement. and our compare to series from 1 to infinity of 1/3 over n diverges, then the sum from 1 to infinity of 1 over n plus 2 diverges by the comparison test. So now, to go back to our original question, we want to know if the alternating series is absolutely convergent, conditionally convergent, or diverges. And let me just make a little extra room here. Scooch these up. Since the sum from 1 to infinity of -1 to the n over n plus 2 converges by the alternating series test, and the sum from n equals 1 to infinity of the absolute value of our terms, so the absolute value of -1 to the n over n plus 2, diverges by the comparison test. Then the series -1 to the n over n plus 2 is conditionally convergent. Okay, so 3 parts to this question. Starting with the alternating series as it's originally given, determine if it converges or diverges. If it diverges, you're done. If it converges, then look at the absolute value of the terms. And if that series converges, then the original alternating series would converge absolutely. And if that series diverges, then the original alternating series converges conditionally. And so then the third part is to give your conclusion statement. Our last series test for the day, in fact, our last series test for the course, is the ratio test. Now, the ratio test is nice because it tests for absolute convergence. So unlike the previous example where we had to break that series up into 2 separate cases, the alternating case and then the absolute value of the terms, the ratio test will determine absolute convergence in one step. So if the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n goes to some finite number less than 1, then we say that the series is absolutely convergent. And if the limit goes to a number greater than 1, then the series is divergent. And then the case where the limit goes to exactly 1, the series could converge or diverge, so it's inconclusive and you'd have to go back and use a different test. The ratio test works because when you're considering the ratio a sub n plus 1 over a sub n, the absolute value of those terms, as n gets really, really, really large, the series begins to act like a geometric series. And in fact, the ratio test should be reminiscent of the geometric series test because for a geometric series, that series converges if the absolute value of r is less than 1 and diverges if the absolute value of r is greater than 1. So very similar premise to that. And so if our limit is either less than or greater than 1, then it's good enough to say it behaves like a geometric series. However, unlike the geometric series, if our limit is 1, then we need more tests because that ratio is to converging or diverging that we can't tell. Ratio test has clues of when you should use it, just like a telescoping series has generally you're looking for maybe a negative sign, or the geometric series is some number raised to a power. The ratio test works really well when you see exponentials and or factorials because they reduce nicely when you divide the term by its next term. Polynomials, on the other hand, they do not work in the ratio test. So like in the previous example, it was a polynomial type series, and if you'd used the ratio test, you would have found that the limit goes to 1, and you'd have to use a different test anyway. So save yourself the time, and if it is a polynomial type series, don't use the ratio test. So let's do an example. Here we have the alternating series -1 to the n times n plus 3 over 2 to the n, and we want to know if it's absolutely convergent. The denominator here, we have 2 to the n, and so that's an exponential, which is our clue to use the ratio test. And just like any of these tests, you want to treat it like it's an essay. So you want your intro, your argument, and your conclusion. So our intro, we name our test. We'll use the ratio test. And our argument, we want to find the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. And a nicer way to evaluate this limit, instead of thinking of it as a sub n plus 1 divided by a sub n, instead think of it as a sub n plus 1 times 1 over a sub n. It will make your math work out much easier. So we have the limit as n approaches infinity of the absolute value of a sub n plus 1. So we would have -1 raised to the n plus 1, n plus 1 plus 3, and in the denominator 2 raised to the n plus 1. And now this is going to be times the reciprocal of a sub n. So times 2 to the n in the numerator, and in the denominator, -1 to the n times n plus 3. Note here that if we got rid of the -1 to the n plus 1 divided by the -1 to the n, then all of the terms would be positive. So we can drop the absolute value signs. And I'd highly recommend, when you are evaluating these limits, to group them by like terms. It makes it much easier to see what's going to cancel out. So we have in the numerator, the n plus 1 plus 3 is n plus 4. And we'll divide that by n plus 3 times 2 to the n over 2 to the n plus 1. And like I said, we can drop the absolute value signs and the -1, and then we don't need either one. So we could simplify the 2 to the n over 2 to the n plus 1. This becomes the limit as n goes to infinity of 1 over 2 to the first power. Your exponential rule tells us that if you have x to the a over x to the b, that is either x to the a minus b, or you could write that as 1 over x to the b minus a. And you'll use that rule a lot when you're simplifying with the ratio test. And that's going to be times n plus 4 over n plus 3. And as it's written right now, this limit is indeterminate. You have it of the infinity over infinity type. So let's multiply both the numerator and the denominator by the highest power term in the denominator, which is 1 over n. And we have the limit as n goes to infinity. You could pull the 1/2 out front if you wanted, or you can leave it in your limit. In the numerator, we have 1 plus 4 over n. In the denominator, 1 plus 3 over n. And now as n goes to infinity, this limit goes to 1/2. and 1/2 is less than 1. So for our conclusion, since the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n and now as I'm writing this, I realize that nowhere on the paper have I defined a sub n or a sub n plus 1. So if I want to refer to the series in terms of a sub n, I need to go back and somewhere on the page explicitly state what our a sub n is. And since I don't want to write everything out longhand, I'll just go back to the beginning and say, next to our ratio test, a sub n is equal to negative 1 to the n times n plus 3 over 2 to the n. And now in my conclusion, it's okay to refer to the a sub n and a sub n plus 1. Okay, so this limit is less than, it's 1/2, which is less than 1. And so the series from 1 to infinity of negative 1 to the n times n plus 3 over 2 to the n is absolutely convergent. By the ratio test. The ratio test works really well when you are dealing with either exponentials, as in the previous example, or factorials. So before we jump into an example with factorials, let's review them. N factorial, so this n with the exclamation mark reads as n factorial, and it's equal to 1 times 2 times 3, dot, 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 all the way up to n minus 1 times n. So if we wanted to find n plus 1 factorial, then we have 1 times 2 times 3, dot, 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 all the way up to n minus 1 times n, and then we stop at n plus 1. 2n factorial, same idea. We start at 1 times 2 times 3 times dot, 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 and now we go all the way up to 2n minus 1 times 2n. It is not the even term, so just note it's not 2 times 4 times 6. What about 0 factorial? Let's start with n plus 1 factorial and see if we can do a little proof to figure out what 0 factorial is. From above, we know that n plus 1 factorial is equal to, this is n factorial if we group together the first n terms. So we have n factorial times n plus 1. So on the right-hand side of our equation, let's rewrite n plus 1 factorial as n factorial times n plus 1. So let's let n equal 0 and sub that into both sides of our equation. 0 plus 1 factorial is equal to 0 factorial times 0 plus 1. So on the left-hand side, we have 1 factorial, which is 1. And on the right-hand side, we have 0 factorial times 1, which is just 0 factorial. And so we've just proven that 0 factorial is equal to 1. Okay, so let's test the convergence of the series from 1 to infinity of n factorial over 5 to the n times n to the 5th. We have a factorial in the numerator and an exponential in the denominator. Either one alone would be enough to tell us to use the ratio test, but with the two combined, for sure want to use the ratio test. Well, we'll begin with our intro, naming our test. the limit as n approaches infinity, and you must have the absolute value signs in the first step, just to show us that you know the actual conditions of the ratio test. So don't simplify it in the first step. N plus 1 factorial over 5 to the n plus 1 times n plus 1 to the fifth. And now we divide that by a sub n, or multiply by the reciprocal of a sub n. So in the numerator, we have 5 to the n times n to the fifth over n factorial. All of our terms are positive, so we can drop the absolute value signs. And this is equal to the limit as n approaches infinity. And combine like terms. So we'll have n plus 1 factorial divided by n factorial times 5 to the n over 5 to the n plus 1 times, I like to leave the polynomial terms for last, so times n to the fifth over n plus 1 to the fifth. Before we evaluate this limit, let's simplify as much as we can. So in the numerator, this n plus 1 factorial is n factorial times n plus 1. We have an n factorial in the numerator and n factorial in the denominator. Those cancel out, and we're just left with n plus 1. Five to the n divided by 5 to the n plus 1 simplifies down to 1 over 5. For the polynomials, as it's written, it's indeterminate infinity over infinity type. So let's multiply through by 1 over the highest power term in the denominator. And so that will give us n to the fifth times 1 over n to the fifth is 1. The denominator distributing, that becomes 1 plus 1 over n to the fifth power. Okay, and so now we can evaluate this limit. As n is going to infinity, the 1 over n goes to 0. And so we have 1 times 1/5 times something that is growing without bound. And so the whole limit goes to infinity. And infinity is most definitely greater than 1. And so by the ratio test, we know that the series from 1 to infinity of n factorial over 5 to the n times n to the fifth diverges. And name your test one more time, just in case, by the ratio test. In the next example, let's take a big picture look at when we should use the ratio test, because like we had said earlier, if you have a series with the polynomial over polynomial, the limit goes to exactly 1, and so it's inconclusive. You have to start all over. For the ratio test, we're looking for exponentials and we're looking for factorials. In the first term, we have a factorial on the denominator, and 2 to the 2n is an exponential. So we would use the ratio test. Top row on the right, we have the exponential in the numerator, we have the factorial in the numerator, and we have an exponential in the denominator. Also a sign of using the ratio test. And the only other one that has either exponentials or factorials would be in the bottom row middle. The 2 to the n over 3 to the n, those are exponentials, and so we'd also use the ratio test on this series. For the other three that we would not use the ratio test on, two of them are alternating. We could use the alternating series test on the top row middle and then on the bottom row far right. And for the remaining one, comparison test. In the examples we've done so far, canceling out the factorials and the exponentials have been pretty straightforward. But in workshop, you're going to get a chance to do some more challenging problems. So I wanted to take a quick second and just go through the algebra when you're canceling out some more complicated type problems. We have 2n quantity factorial, and we want to simplify a sub n plus 1 over a sub n. To begin, just anywhere we see an n, we'll replace it with n plus 1, and that will give us our a sub n plus 1. So we have 2 times n plus 1 and factorial, and then in the denominator 2n quantity factorial. Let's simplify. We'll distribute the 2 in the numerator, and this becomes 2n plus 2 quantity factorial over 2n factorial. And to cancel out, let's start writing it out longhand. In the numerator, we have 1 times 2 times 3 times ... all the way up to, we'll write out a couple of the n terms here so we can see what cancels. So we'll start with 2n minus 1. The next term we add 1, so 2n minus 1 plus 1 is 2n. 2n plus 1. And finally 2n plus 2, which is where we stop. In the denominator, we have 1 times 2 times 3, ... all the way up to 2n minus 1. Now we add 1 to that, so 2n minus 1 plus 1 gives us 2n, and we're done. So canceling out, we see that everything in the numerator cancels with everything in the denominator, except for the last two terms in the numerator. And so 2n plus 2 factorial divided by 2n factorial simplifies down to 2n plus 1 times 2n plus 2. In example 7, now we have exponentials instead of factorials. So to find a sub n plus 1, we substitute n plus 1 in place of n. So we have 3 raised to the 2 times n plus 1 over 3 to the 2n. Simplifying in the numerator's exponent, we'll distribute that 2. So we have 3 to the 2n plus 2 over 3 to the 2n. And we have an exponential rule that tells us if you have x to the a plus b, you can rewrite that as x to the a times x to the b. So in the numerator, we can rewrite 3 raised to the 2n plus 2 as 3 to the 2n times 3 squared. And that's all over 3 to the 2n. The 3 to the 2n's cancel out, and we're left with 3 squared, which is 9. Now we have 3 classifications of series. Absolutely convergent, and keep in mind that any series who has all positive terms is by default absolutely convergent, conditionally convergent, and divergent. So one of the big differences between absolute convergence and conditional convergence is it lets us know when it's okay for us to rearrange terms and when we can't. So let's consider the conditionally convergent series below. This is the alternating harmonic series, and as we will learn in the upcoming weeks, the series converges to the natural log of 2. Let's manipulate this series a little bit and see what happens. I'll call this first line equation 1, and now we will multiply through by 1/2. When we do this, we have 1/2 minus 1 plus 1/6 minus 1/8 plus 1/10 minus, and so on. And then on the right-hand side of our equation, multiplying through by 1/2 gives us half natural log 2. This is our equation 2. And now let's place 0 in between all of the terms. Just drawing little lines here so I can keep straight where we are. So placing 0 between the terms, and we'll start with the 0. So here we have 0 plus 1/2 plus 0 minus 1/4 plus 0 plus 1/6 plus 0 minus, and we can continue the pattern. Let's line up our terms here. And now for our final step, let's add equations 1 and 3. I forgot on the right-hand side of the equation, even adding 0 between the terms, we still have 1/2 the natural log of 2. Okay, so now let's add equations 1 and 3 together. So we have 1 plus 0, so our first term here is 1. Then we'd have a minus 1/2 and a plus 1/2, so plus 0. Plus 1/3 plus 0, so plus 1/3. Minus 1/4 and minus 1/4, so minus 2/4, which simplifies to minus 1/2. For our next term, we have a positive 1/5 and 0, so plus 1/5. Next term, we have a minus 1/6 plus 1/6, so those cancel out and give us 0. And the next term is 1/7 plus 0, so plus 1/7, and we continue the pattern, and then on the right-hand side of our equation, adding the first line and the third line is 3/2 natural log of 2. But if you go back and you look at the left-hand side of this equation, we have a 1 minus 1/2 plus 1/3. Somewhere down the road, the next term here would have been a minus 1/4 plus 1/5. We would have ended up with a 1/6 out here somewhere. And you can see that this line here is the exact same terms as in the first line, just rearranged, which then basically would be saying on the right-hand side of our equation that the natural log of 2 is equal to 3/2 the natural log of 2. Or if we divided out the natural log of 2's, we would have just proved that 1 is equal to 3/2. Clearly not so. So the issue here is that the original series, the alternating harmonic series, is conditionally convergent. And so if a series is conditionally convergent, any rearrangement of the terms could be manipulated to be equal to any real number. And so for conditionally convergent series, you cannot manipulate the terms. That you have to leave them in the order that they occur in the series. However, if you have an absolutely convergent series, then you can rearrange the terms however you like, and they will always still sum to the same number s. So one of the big differences between the absolute convergence and conditionally convergent series is allowing you to know when it's okay to rearrange terms and when you can't.